Okay, so let me see. Last time we stopped, we had just done an example of a polynomial inequality, and I'm going to do one more example of polynomial inequalities, and I'm actually going to move on after that, and nothing after polynomial inequalities is going to be in your course anymore. There's just a little too much to get through. So we won't be doing rational inequalities or graphing polynomials and rationals and things. The way that we have to graph them without doing it properly with limits and with calculus is a little, I'm not the biggest fan of it myself, but I teach it anyway. But it's a little awkward. So I'm just going to cut it out of the course for you so you have a little less to worry about. And after I do another example of polynomial inequalities with you today, that will be the last thing from that chapter, which I think is chapter 4 that you have to cover. We're going to move right on to exponents and logs today as well. And one other thing to note as well is that your quiz will cover everything from last class and this class, or it can cover everything from last class to this class. Since your midterm took the place of your quiz last week, I'm going to use that to put a question or two onto your quiz this week. So it's still the same amount of questions. It'll still be just, I think it's 5 questions, but it'll cover classes 4 and 5. So just on the side, I'm going to write here for you. Quiz this week covers classes 4 and 5. Every week so far, it's been that I do something on a Tuesday and then you have some questions on a Friday on that content, but this stuff, it can be the previous week too. I just published your assignment scores on Gradescope, so you can log on to gradescope.ca, I assume, and check out your score there. If you have any questions or anything, email me. Don't ask me during class because I won't have time to look at it and talk to you about it. So if you have any questions or concerns, you can email me. I'll be releasing your midterm grade soon as well. I did have a typo in one of the midterm questions, so I'm actually just going to give everybody 5 out of 5 for that question. In the last question, you had to solve a polynomial. I think it said something like, given that x equals 2 as a root, solve the polynomial x cubed and so on. But I think I should have had negative x squared, not negative x. I think I had minus x minus 9x plus something. It should have been minus 8x squared plus 9x or whatever it was. So that messed up the question a little bit, and it made it very, very hard to solve. You're supposed to use long division, so I'm just going to give everybody full marks for that question. To anybody that managed to solve it, you might as well be aware that I'm now suspicious of you because you needed a computer to do it. Or anybody aside from those who came in and asked me about a typo, and then I told them about the typo into the Google Meet call. So, okay. Yeah, that's fine, Lewis. I know a few of you asked me. Okay, so one more polynomial inequality to remind you how it works. And here we go. So let's say we have to solve x to the 4 minus 2x cubed greater than or equal to 4x squared minus 3x. Okay, I'm actually teaching this class from Ireland today. I'm a home visit in my family, so I have a fake background because I'm in my parents' spare bedroom right now in this class. Thankfully, they have good internet, so there shouldn't be any problems with today's class. So it's 3 o'clock here. I've just beaten the jet lag, I think, so we should be okay. Okay, so we covered this last week, but I doubt you paid much mind to it after the last class because it wasn't something that I told you was examinable. I told you could have got anything up to rational equations in the midterm, and this came after rational equations. So I would say that you might not remember this too well. So I'll go nice and slowly over this one. Will there still be 5 questions? The quiz? Oh, the midterm that you just did? The midterm, you mean? Or the quiz? Oh, the quiz on Friday? Yeah, I think there's 5 questions. So it's not like it'll be an extra long quiz or anything just because there's 2 weeks, double the length, double the amount of questions kind of thing. I've just picked some questions from last week's class as well, and some from this week's class. So no, it's not like it's extra long. It's about the same length as all the other quizzes. Okay, so first thing we want to do with these is to get everything non-zero on one side of the equal sign. So the first thing we want to do is bring the 4x squared and the minus 3x across. And as with most things that we've covered in this course, the first step is often to try to factor as much as possible, see what we can get to work. So first thing we want to do here is common term factoring. And our next thought would be to say, let's look at this thing here and try to factor it further. We're looking at that thinking factor by grouping might be something that we can try, but it doesn't appear that will work here. We can't think of a way to group them. So what we actually want to do is find the zeros of the equation. So I'll just remind you that before worrying about, about solving the inequality, we have to solve the associated equation. So meaning that we're just going to drop that inequality symbol and solve it as an equation first to see where it's zero or see where the polynomial crosses the x-axis. So first what we're going to do is solve x times x cubed minus 2x squared minus 4x plus 3 equal to 0. We'll worry about the inequality in the end. Okay, so when we have two things multiplying by 0, the solutions are that one of those things can be 0 or the other one. Okay, so here's one of our solutions. X equals 0 is the solution to the equation. The other solutions are tied up in that polynomial right there. So what do? We start to guess solutions to it. This is something that I wanted you to have to do in your midterm on question 6, but I messed up the question, so it wasn't to be. I'll probably put it on your final then, since it wasn't on your midterm. So there's if I remember. I haven't made the final yet, so right now it seems like a good idea, and I would probably put it on the final, but don't quote me on it because when I make the final in a week and a half, I might forget. But right now it seems like a good idea to put a question like this on your final. Anyway, let's test some solutions in here to find one, and then once we found the root, that means we know a factor, and we can do long division and solve the equation that way. Okay, so next step is to try to find a root by trial and error. So let's try x equals 1. 0 clearly doesn't work, so let's start with 1. 1 cubed minus 2 by 1 squared minus 4 by 1 plus 3. Is that equal to 0? I see plus 4 and I see minus 6 in there. That is not 0. Let's try x equals negative 1. Minus 1 cubed minus 2 by minus 1 squared minus 4 by minus 1 plus 3. This looks like it doesn't work as well. You can double check any of these if you want, but I'm looking at this and I'm thinking that's not going to give us a root. So I'm going to just say no and move on. I don't need to find the exact number. If the answer is 3 or 4 or minus 2 or something, I don't actually care about that. All I care is that it's not 0. So once I see something that does not appear to be adding up to 0, I'm just going to go not and move on and stop doing that mental addition or whatever. See if I can do it. Okay, 2 cubed minus 2 by 2 squared minus 4 by 2 plus 3. So 2 cubed is 8 minus 8. This is not going to, whatever is left is not going to add to 0. So again, I move on. Let's try minus 2. Minus 2 cubed minus 2 by minus 2 squared minus 4 by minus 2 plus 3. Minus 2 cubed is 8. No, this is definitely not going to work. I have a whole bunch of negative ones and only a positive 3. So here I have minus 8 in here. Plus 8. Oh, no, sorry. Plus 8 is 0. Oh, no, here I have negative 8 or something. It's not going to be 3 anyway, so it's not going to work. Let's try 3. 3 cubed minus 2 times 3 squared minus 4 times 3 plus 3. It's getting a little harder to do it now, so I might have to do this one out. 3 cubed is 27. 3 squared is 9 times 2 is 18. Minus 12 plus 3. This looks good. The positive numbers add to 30. The negative numbers add to negative 30. So that one is a root. So x equals 3 is a root. And that means that x minus 3 is a factor. That was by one of those theorems we covered last time, the factor theorem. Okay. So once we found a root, we found a factor. And what's next is to do some long division. So we're going to divide x minus 3 into x cubed minus 2x squared minus 4x plus 3. Dividing in here, we get x squared minus 3x squared. So changing signs to do my addition here. 3 minus 2 is 1. Divide x into x squared and I get plus x. Multiplying the x by x minus 3, I get x squared minus 3x. Changing my signs. I'm left down here with negative x. X into negative x is negative 1. And negative 1 multiplied by x minus 3 is minus x plus 3. This looks good. So we're going to get 0 as our remainder, like we would hope. Because if x minus 3 is a factor, if you divide a factor into something that it's a factor of, you should not have a remainder. So it's a good thing that we're seeing a 0 remainder here, because that kind of makes me just confirm as I'm going down it. Yeah, this is going okay. That should be a factor. So I've almost confirmed to myself that x equals 3 is a root because x minus 3 is a factor. So the other solutions are going to be tied up in here. So what I have to do is solve this for the other solutions. Okay, what do we get? I think I'm going to have to use the minus b formula here because factoring won't work. So I'm looking at minus b plus or minus the square root of b squared minus 4ac all over 2a. Wait, can I factor this? Square root of 9 is 3. B squared. No, I am wrong. Sorry, I've made a mistake. Minus 4 times a times c should be just plus 4, not plus 8. So it won't actually be a nice answer, kind of like I was expecting. So this is minus 1 plus root 5 over 2. And also minus 1 minus root 5 over 2. So the square root of 5 is just, I guess, a little bigger than the square root of 4. So it's probably like 2.1 or something. So 2.1, 1.1. It looks like about 1.1 over 2. And the other one is something negative. So now what we've done is we found all solutions. So all solutions to the equation, originally it was x to the 4 minus 2x cubed minus 4x squared. Minus 4x squared? Yeah. is equal to 0 are. So if you remember, back up here, this was the first solution that we found up here. It was x equals 0, because the first thing we did was we factored out 0, and then we had the polynomial to solve. The next solution that we found was x equals 3. That was by trial and error. So those are two of our solutions. And the last two solutions that we found were this one here and this one here. So we're putting all those together, and we have x equals 0, x equals 3, x equals -1 plus root 5 over 2, and x equals -1 minus root 5 over 2. Those are 4 solutions to the equation. And the reason that we wanted to solve it, if I can go back here, the original question was about solving an inequality. And I kind of took you aside and said, well, okay, before we worry about the inequality, we have to know where that expression on the left is equal to 0 first. The idea being that, let me just draw something quick here before I get into it. The idea being that, let's say I have some polynomial that's doing this here. Now, this is not an accurate drawing of what I just have. But what I want to do is figure out where it's 0 first. Because if I know where that is, 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 those are all the places where it's 0. Everywhere else, it's either positive or negative. So back here, it's negative. Here, it's positive. Here, it's negative. Here, it's positive. Here, it's negative. Here, it's positive. Because here it's negative because it's always going to be below the x-axis here. It's positive because it's always above the x-axis here. Negative in this region because it's below. Positive in this region. So the reason I wanted to know those zeros was because that tells me what the intervals I should have are going to be. I'm really looking for these intervals, because if the question says solve where it's bigger than 0, I'm going to pick out the positives, and then whatever these intervals are here, that's going to be part of my answer. So before you even worry about the inequality, it's the zeros that matter. It's these places here where it touches the x-axis, and that's what we just solved. Those numbers that you see on the screen just above there, 3, 0, -1 plus root 5 over 2, -1 minus root 5 over 2. Those are those red dots that we've just found. So now what we have to do is find out which places around those red dots are, what was the question again? I've forgotten. Bigger than 0 was the question. We were asking for greater than or equal to 0. So we're going to be looking for the positives here. Okay, so where was I? Right, okay, yeah, so what we want to do is think of the number line, but with those numbers that we've just found, kind of separating it all out for us. The first of all these numbers is going to be -1 minus root 5 over 2, because that's the furthest to the left number that we found. -1 minus root 5 over 2. Next will be 0. Next will be -1 plus root 5 over 2. Oh, sorry. Plus root 5 over 2. And over here we have 3. So, okay, for convenience, what I'm going to just do is search what exactly is -1 minus root 5 over 2, just as a decimal, because it's a little easier to. So this is minus 1.6, and the other one is 0.6. That's just a little more convenient to think of what the intervals are going to be. Okay, so what I'm now thinking about is I'm going to make that table that we did in the last class. Remember the table where we were filling in plus signs and minus signs and then multiplying them together? So all the factors of this thing are going to be like this. So what we want to solve, the original polynomial that we had, and I'm going to write it in its factored form now. It's -1 minus root 5 over 2, and x -1 plus root 5 over 2, greater than or equal to 0. So that's what we're trying to solve. Using all those roots that we found, I'm rewriting it into its factored form. And these intervals up here, minus infinity to minus 1.6. I'm going to stop writing the radical form of it because it's a little big to write all the time. So I'm just going to use the decimal form from here on out. Minus 1.6 to 0, 0 to 0.6, 0.6 to 3, and 3 to infinity. Okay, so we're going to go to the table that we made before. I'm going to write in those intervals. We're going to write all our factors down the table here. Any questions so far? No one's asking me anything. That worries me sometimes. Good. Okay, so if you remember what we do for this, you pick a random number inside each of those intervals on the top. So let's pick, say, -5 in here. Let's pick -1. I guess 0.5 would work here. 0.6 to 3, let's pick number 2. And 3 to infinity, how about 10? Any random number in those intervals are what we're going to think of mentally. So if those numbers that I have in blue at the top, if I plug them into what I'm thinking of is, say, each of these factors on the side, is the result positive or is the result negative? Well, if I plug -5 into the first factor here, it's going to be negative. -1 in its negative. And then 0.5, 2, and 3, they're all positive. If I plug it into the second term here, the x minus 3, -5 minus 3 is -8, which is negative. -1 minus 3 is negative. 0.5 minus 3 is negative. 2 minus 3 is negative, but 10 minus 3 will be positive. This is how I'm making the signs for this table. Plug in -5 into the next factor. -5 minus 1.6. Go ahead, Lewis.
Are you sure that in the x minus 1.6, it shouldn't be like x plus 1.6?
You're right. It's minus 1.6, isn't it? Thank you. Yeah, you're absolutely right. So thanks for that. Let me just correct that. So for anybody that didn't catch that, I didn't write my factor incorrectly, because if you remember, this one here is -1.6. My factor should be x minus 1.6, which would be x plus 1.6. So that one there is incorrect. This one here is okay. This one was 0.6. So that's just x minus 0.6. But Lewis is absolutely right. The first one is plus 1.6 instead of minus 1.6. So I have to be careful when I'm doing this one. -5 plus 1.6 is still negative, but -1 plus 1.6 is positive. Yes, and the rest of them are going to be positive as well. And then x minus 0.6, so -5 minus 0.6 is negative, -1 minus 0.6 is negative, 0.5 minus 0.6, that one is still negative, but then 2 minus 0.6 is positive. And okay, now multiplying the signs of all those factors in the various regions, we have, in the first one, we have minus by minus by minus by minus. That will all multiply to give me a plus. The second one has 3 negatives, which multiplies to give me a negative. The last one has 2 negatives and 2 positives, which is going to multiply together to produce something positive, negative, and positive. So I'm ready to give the solution now. And the solution, we're going to give an interval form again. What we want is, we want the greater than 0. So we're looking for that, and that, which means we're looking for this interval, and this interval here. And since it's greater than or equal to 0, we're going to use hard brackets wherever the thing equals 0. Okay? So the solution that I'm going to give in interval form, minus infinity to minus 1.6. That was a place where it's 0, so I'm going to use a hard bracket. 0 to 0.6. And 3 to infinity. You always use the soft brackets at infinities. So that's my final answer to this question. That was a longer polynomial inequality question, a bit longer than expected. Any questions here? That's about as hard as it gets, I think. That one, you had a bit of work to do to solve where it's equal to 0, long division. You have to do all that kind of stuff. And there were 5 intervals here, so it was a little bigger to work with, a bigger table, 4 factors and 5 intervals. So I think that's about as hard as it's going to get for you for this topic. How do you feel about this one? That thing you do in the chat, 1 is if you don't get it at all, 5 is if it's perfect, and 2, 3, and 4 in between. Can you write down what you think? 3.7. Very specific. Okay. Yeah, I'm happy enough with that. A couple of people lingering around 3, but it really just takes the practice of yourself to move a 3 into a 4 or a 5. For anybody that is towards the lower end here, the 3s or the 3.5s, any questions? Haji, Jasmine, who else? Evan, Jamal? From you in particular, any questions? Was there something about this question you weren't sure of in particular, or if it's just a sense of, I wish I could see more or need to practice? Exactly, doesn't. Okay, that's good. We get time for practice anyway. Yeah, just to the practice. Yeah, so definitely have a read over. I'll post the video and you can watch over this one again. The part leading to the final answer. Okay, so if there's something specific, that's good. Jamal, do you want to unmute and say whereabouts it sort of gets a bit?
Like after the table where you used minus and plus signs to.
Yeah. Is it actually getting the minus and plus signs, or was it writing down the answer?
Writing down the answer.
Writing down the answer. Okay, so I chose the plus signs because the question asked for greater than or equal to 0. So that's why the plus signs were selected. If that was less than 0, I'd be selecting the negative signs. And those plus signs corresponded with the minus infinity to minus 1.6, the 0 to 0.6, and the 3 to infinity intervals. So I know that those intervals are going to be the answer. So the next part really is just about choosing those things. I'm guessing that's where you're a little unsure. Well, this question asked for strictly greater than 0. Now, it asked for greater than or equal to 0. If it asked for strictly greater than 0, what I would then say is the polynomial being equal to 0 is not allowed. It's equal to 0 at negative 1.6, 0, 0.6, and 3, because that's what we solved in the long division and the factoring and everything. So if it was a strictly greater than 0, not allowed to be 0, I would use these brackets and say, because you can't have those numbers in your final answer. But since this question said greater than or equal to 0, I'm going to kind of modify the things from the table and say, well, negative 1.6 is allowed, 0 is allowed, 0.6 is allowed, and 3 is allowed. Because if we go back to our original thing here, where is it? Okay, let's say we look at it up here, this equation up here. Maybe the one above that, actually. Like if I plug 0 into this equation, I would have 0 multiplied by everything else, which makes it equal to 0 on the left side. So what I will be looking at is 0 bigger than or equal to 0? Yes, it is. So 0 is allowed in the equation. But if this was a question where it was strictly greater than 0, then I would say, oh no, I can't have that. 0 isn't bigger than 0 because it's equal to 0. So that doesn't work. 0 is not an answer that's allowed. And I would use soft brackets to give the answers. So that's why I changed some of those to hard brackets. It's because the zeros are allowed in this case. Okay, so we're going to move on now to exponential functions. I think what I will do is share something from the book. So I haven't got my usual setup this time. Go ahead, Evan. I was wondering if we were able to see our assignment marks in Gradescope. They should be displayed. I thought I clicked to publish the grades already. I'll double check it after this to make sure that they're available. But you should be able to see it if you log into Gradescope. That's oh. Let me just double check something here. Yeah, they're published. Just make sure you're logging in with the correct email. It's the email that I have for you on Gradescope. It starts with a K, K-I-T. Oh, you can't either. Okay, I'll double check that after class today and just make sure that I'll try to figure out what's wrong. I think you should be able to see it, but I don't know why you can't. Because I have the option to unpublish them, which would imply that they're currently published, and I click publish to do it. So I'll double check it and see if there's something I can do to make you see it. And I'll post an announcement about it as well once I have it sorted. I don't know what's causing that. Okay, so yeah, we're going to move on to exponential functions now anyway, and I'll try to have your assignment grades available after this. So a bunch of people can't. Is there anyone that can see them? If you can see your assignment grades or have seen it already, just click yes. And don't go searching now if you're paying attention here, but I'll look back later and see that anybody said that they can. I'm guessing that nobody can. If half of you can't. Okay. Okay, so let me share screen here. Ungraded. No, they're definitely graded. Yeah, I'll try and find out what's going wrong with that. I don't know what it is. Okay, so we're going to look at exponential functions and their graphs now, and we're going to use 2 to the power of x to kind of explore it and see what it's all about. I hope that you're mostly comfortable with exponential functions. It's a topic that you'll definitely have covered before, but just to go over it again. Okay, let's talk about first how to just set up the graph of it and what it looks like. So looking at a bunch of numbers close to 0 and just seeing where they go. Let's start with 0 here. 2 to the power of 0 is 1. So you'll notice that if you go to x equals 0, which is in here at the axis, 2 to the power of 0 equals 1. So right here where my cursor is, that's going to be a point on the curve. 2 to the power of 1 equals 2. 2 squared equals 4. 2 cubed equals 8. So the curve is going to travel up through all those points, and all the numbers that are harder to do in your head, like 2 to the power of 1.4 or something, they're all the numbers in between. And going backwards, 2 to the power of negative 1. So that's something that you might remember about. So we've kind of used that a few times in the algebra, but 2 to the power of negative 1 is the same as 1 over 2 to the power of positive 1. So it's like if you bring a number below that denominator line, below that line, a positive exponent becomes a negative exponent. So 2 to the power of negative 1 is the same as 1 over 2 to the power of positive 1, which is a half. Likewise, 2 to the minus 2 is the same as 1 over 2 squared. 2 to the minus 3 is the same as 1 over 2 cubed. So you'll notice that these numbers get smaller and smaller and smaller, but they won't go below 0. They'll just be very, very tiny fractions the further back you go. So we have this graph that further and further back, it's extremely close to the x-axis. We'd have to really zoom in, for example, to see what 2 to the power of minus 10 would be. Because it's such a tiny fraction, to our naked eye, we probably couldn't see the difference between the x-axis, but it's a tiny bit above if you zoomed in enough. As we get closer to 0, it begins to come off the axis, and then it shoots up really fast. So other graphs will look like this too, 3 to the x, 4 to the x, 5 to the x, except they'll shoot up quicker, and they'll get flatter a lot quicker as well. So they just are a little more extreme than 2 to the power of x. So some of the things to note here, the further we take it towards minus infinity, the closer 2 to the x gets to the 0. And as you increase x, 2 to the x gets very, very large, and it starts to go really high. And some of the features that I think we mentioned nearly all these. The domain for exponential functions is minus infinity to infinity, because any number you want, you can plug it into the function and you don't have a problem. All numbers are in the domain for exponential functions. For the range, well, you can just look at the graph. As we talked about already, it's never going to be down onto the graph. It's never going to get, down onto the x-axis. It's never going to go below the x-axis either. So 0 won't be in the range of it, because you can't actually reach 0. You just get close to it, but never actually getting there. You're never going to go negative. So the range is going to be everything from 0 to infinity, but not including 0. At y-intercept, you can see it here. It's at 0, 1. There's no x-intercepts in this graph, because we talked about how it won't touch the x-axis ever. Now, with certain transformations of the function, you might shift it down, and then it'll have an x in. The range is going to change, and there'll be an x-intercept and things like this. But as we see it now, just the basic exponential function of number to power of x, these features are true. We do have a horizontal asymptote. I guess we didn't do asymptotes now, since I skipped the graphing section for you. Does everyone have an idea of what horizontal and vertical asymptotes are? I think those. Okay, good. I never really like talking about asymptotes in this course, because to do it properly, we should be using limits. But I'm saving limits for calculus, because you'll do limits fully in calculus anyway. And I would rather not have to dedicate so much time to it. But that's good that you have an idea that what a horizontal and what a vertical asymptote are. So there is a horizontal asymptote. It's the x-axis, which is the line y equals 0. And there's no vertical asymptotes for exponential functions. So these are just features to remember about this graph. Yeah, so as I was mentioning, for numbers bigger than 2, if you have 3, 4, 5, or 10 or whatever, the graph just becomes a bit more extreme. So if you can see the blue dotted line here, it increases more quickly after it goes through this 0.1 here, and it decreases a little faster than the red line. And if you have numbers smaller than 2, for example, 1.5, 1.4, 1.3, 1.8, they will increase more slowly, but they will also decrease more slowly on the left side of that y-intercept as well. So that's just how the graph is a little bit. Other than that, all the features are the same. You're going to have the same asymptotes, the same intercept of y equals 0, because anything to the power of 0 equals 1, whether it's 2 to the power of 0, 3 to the power of 0, 1.5 to the power of 0, all those are equal to 1. So you're always going to have that same y-intercept. No x-intercept. You have the same asymptotes, same domain, and same range. But it just looks a little different. It's just the steepness of it kind of is what's affected by changing the base number. And what we haven't talked about yet, though, I was talking about different numbers, and I didn't go below 1 on purpose. I didn't want to talk about fractions because they're a little more complicated. So here we go. What about something like a half to the power of x? Well, this is going to be a little strange looking once you see it. But one thing that you can notice to help you kind of understand why this happens is that you can look at a half to the power of x as 1 over 2 to the power of x by distributing that power of x onto the top and onto the bottom. And remember what we said earlier about 2 to the power of negative 2, 2 to the power of negative 3, and so on. That was the same as 1 over 2 and 1 over 3, and so on. We can do the same thing in reverse. So what we can do is bring that 2 to the power of x above the line, and it's going to become 2 to the power of minus x. Now, Now is when I'm going to call you back to your transformations. Remember one of our transformations, we said that if you do f of x to f of negative x, that represents a reflection over the y-axis. So 2 to the power of x being transformed to 2 to the power of negative x. That's like if you start with 2 to the power of x and mirror it over the y-axis and see what you get. So what you're actually going to get is this graph down here. Okay, so for numbers bigger than 0 but smaller than 1, the graph is like it's been mirrored over the y-axis, and it's going to decrease to the right and increase up to the left. That's something you should probably spend a little bit of time thinking about and subbing in numbers and getting a sense for why the numbers are the size they are, and why that's going to be true for all the numbers between 0 and 1, for example. Just something to think about here. So a little different. When a is between 0 and 1, it decreases to the right and increases to the left. And when a is bigger than 1, that's the base of it, it increases to the right and decreases to the left. And the last thing that I never talked about are where the base is equal to 0 or the base is less than 0. That would not be a very nice function, because, for example, think about if you were to think of a square root of numbers. That would be, or a fourth root or something like that. Anything where you have kind of a square root of a negative number is going to be a problem, because your graph won't be defined in for a whole lot of places in a whole lot of numbers. It'll be a really weird graph and it won't work. So we never really talk about exponential functions having negative bases. The function is just going to be kind of messed up and it won't really work. So the only bases that you think about for exponential functions are between 0 and 1, but not equal to 0. You don't really think about 1 either, because 1 to the power of anything will always stay as 1, and all you'll ever have is a horizontal straight line. It's not exponential. It doesn't have that exploding kind of graph to the right or the left, depending on the size of the number. So it's not really an exponential function. It'll just be a straight line. So you never really think of exponential functions as having a base of 1, because it wouldn't be an exponential function anymore. It would just be a line. But then you also think of them being bigger than 1, like 2 to the x, 3 to the x, and so on. Okay? So are there any questions right now before we move on about exponential functions? Any you remember from school maybe that you wanted to just ask about or clarify or something? Or did I challenge an understanding that you had of it that you're not sure about something right now? You all good? Okay. I'm just going to go back to share the screen again here. Okay. We don't have to graph these. IG, so yeah, I might ask you to graph it, but only in the context of transformations, which we've done. The graphing that I left out was from graphing rational and polynomial functions, because it would just take a little too much time to get through them all and maybe make the course a little too hard to digest all the information before the last class. But for exponential functions and logarithmic functions, yeah, you literally just have to remember that it looks like this, and the same shifts and rotations apply. A shift to the right, down, a stretch, and so on. It's those transformation style graphing. So we did cover this. Okay, so what I'm going to go through now are the properties of the exponential functions, or properties of exponents, I should say. Properties of exponents. So now a bunch of these properties you have already seen, so they're nothing really to worry about. It's going to be kind of a reminder. So this is for, I should state that this is for A and B positive, A and B not equal to 1, and X and Y being real numbers. then we have these properties. So you have a to the x multiplied by a to the y. That one is equal to a to the x plus y. Now this is something that you've probably seen before. So just as a quick example, I'm sure you've all done this for me in various quizzes or assignments, but if you see like x squared times x cubed, your instinct is going to tell you that's x to the 5. And that's because you do 2 plus 3 to make 5. So this is just to provide some formality of running over these properties that I think you already know. If you have a to the power of x to the power of y like this, well, what do you do when you have a power of a power? You multiply the powers. So again, for an example, if you have x squared cubed, I think most of you would probably tell me that is x to the power of 6, because it's a power of a power, so you multiply them. This is also a property. Let's say we have ab to the power of x. That is a to the x, b to the x. I think that's something that you probably did for me a lot already as well. Let's say you have x times x minus 1 and it is all cubed or something. Well, if need be, you can rewrite it this way. I think there's definitely been a case or two where we did that, so that should feel familiar too. It works for division as well. If you have a over b to the power of x, that power can be distributed onto the numerator and onto the denominator. So again, as an example, I think I did it with 1 over 2 to the power of x a few minutes ago. But let's say we had x over x plus 1 to the power of 4. You can say that that's x to the 4 over x plus 1 to the 4. Let's suppose you have a to the x over a to the y. Well, when it's division like that, you might remember you subtract the powers. So for example, this one might be seen, if you see something like this, x squared, x to the 7 over x squared, you would probably say, well, oh, if I want to sort that one out, I'll bring the 2 above and it becomes a minus 2. So 7 minus 2 is 5. Now, there's a few other ones here that I'm going to say that you probably would have guessed them or something, but I'm going to formalize them here because you're going to use them to solve some exponential equations, which we'll do in a minute. If you have a to the x being equal to a to the y, that can happen if and only if x equals y. So for example, let's say you have 3 to the power of x minus 1 is equal to 3 to the power of 2 minus 2x. Well, then what you're going to say is that means that the x minus 1 must be equal to 2 minus 2x. That because these powers are the same, I can apply that property number 6 and say, okay, if those powers are the same, sorry, if those bases are the same, then, and if they're equal, then the powers must be equal as well. That's the only way that that equation as a whole can happen. So that's something that you're going to use from time to time. And the 7th one, provided that x is not 0, then a to the x is equal to b to the x implies that a equals b. So this time, if it's the powers that are the same, you can equate the bases. So for example, if you have, let's say you have x minus 1 to the power of 5 is equal to 2x plus 3 to the power of 5. Well, since the bases are the same, and since the base is not equal to 0, that means that x minus 1 is equal to 2x plus 3. And you can solve from there. Okay. So those last two are two rules that you're going to use if you're trying to solve particular exponential equations. And for anyone that remembers exponents and logs well, in a lot of cases, it's actually just more convenient to use logs to solve for exponential equations. But we're going to start off without logs, and we'll get to logs before the end of this class, but we're going to go back to a reminder of, solving some exponential equations. Some other things to note as well. So some other important notes about exponential equation. X to the power of 0 is always equal to 1 for all x in real numbers. X to the power of 1 is always just going to be equal to x. 0 to the power of x is equal to 0 for all x. And also 1 to the power of x is always just going to be equal to 1 for all x in the reals. Are there any questions so far? Oh, maybe you haven't seen some of that notation before. So let me just put the notation on the side here. This upside down A that you're looking at, it means for all or for every. This kind of strange looking E, let me just make sure that it's written correctly, since this is the moment that you're probably trying to learn it. It's like a C, but with a line in the middle. I interpret that as is an element of. So for every x is an element of, or which is an element of, is what I use for that. And this R with the bar beside it means real numbers. So those are the rational numbers, the irrational numbers, and everything else. Actually, that is everything. The rationals and the irrationals. Okay. Are there any questions about anything so far? This is kind of an aside, so I'm just going to box it off here. You're familiar with what rational numbers, irrational, natural, integers, you're familiar with all those number groups? What they are? Okay, very good, very good. They didn't, irrational numbers weren't believed to be possible for the longest time by mathematicians, way back, I mean. So an irrational number is a number that cannot be written as a fraction. So for any number that you'd say to me in words right now, it's probably a rational number, unless you just say pi, for example, or e. But let's say you're saying to me, can you write 2.7138249 as a fraction? I think, yeah, I can. I'll move the decimal point over and I'll divide it by whatever it might be, 100,000 or a million or something, and there it is as a fraction. But mathematicians didn't think irrational numbers were a thing. They thought that, they believed that every number was rational, even if you weren't able to do, maybe you're not able to do it, but it is rational as kind of a belief. And who was it? Somebody proved that the square root of 2 is an irrational number, that it's not possible to write it as a fraction. And supposedly he was drowned for it, because it was so outrageous that he would prove that it wasn't possible. People drowned him. So yeah, it was a sensitive subject for a while about whether irrational numbers are possible. I think math and philosophy were a little more intertwined in some ways, and religion almost, and things like this. And people would think that, if the world is made to be this logical place with beauty and symmetry and everything, that it's nice if every number can be a rational number. But yeah, that was one of the stranger things that happened in the history of maths, supposedly. And it's not even that hard of a proof. I could probably run through the proof and I think most of you would understand it, for square root of 2 being irrational. It comes down to prime factorizations. Does prime factorization ring a bell with any of you? We did a little bit of it when we went through radicals. The idea is that every single number can be written as a product of prime numbers. So for example, if you tell me, say 32, I can always keep breaking this down to be a product of primes. So this is, oh, that's a silly one because that's 2 to the power 5, right? But every number can be written as a product of some of the numbers, say 2, 3, 5, 7, 11, and so on. And that every number has a prime factorization. So if you're talking about the square root of 2, the idea would be you would, in order to prove it, it looks something like this. It goes, suppose that this can be written as a fraction where a and b are integers. So, okay, and what you would do is you go ahead and you say, well, okay, let's suppose that it can be done, that it can be written as a fraction. And then you take some steps that you're going to say, well, this is clearly a step. You agree that this is true. I can multiply across by b. You agree that I can square both sides because these are things that we do. So it comes down to saying, okay, well, if these two numbers are equal, then their prime factorization on the right has to be equal to the prime factorization on the left. Now, what you're going to do is say, okay, well, let's suppose that the prime factorization on the left has a 2 in it. There must be an even number of 2's because that part is squared, and it's going to be either 2 squared, 2 to the 4, 2 to the 6, 2 to the 8. If there's a 2 in this b here, that's going to be an even number, but this 2 would make it odd. It would make an odd number of 2's on the right, but it has to be an even number of 2's on the left. If there's no 2's in the a's or b's, then you're going to have a 2 on the right side and no 2 on the left. So the numbers can't be equal. The proof goes a little something like that with a lot more formal writing. Do you understand? That makes sense? Maybe it's a little much. I hope somebody got it though. Anyone follow it? Maybe not. No worries. It's not a tough proof though. So if you wanted to have an example of a math proof that from before that you will actually understand and it won't be too deep, that's a nice one. Prove that the square root of 2 is irrational. If you wanted, you could take a look at it and see can you understand it in your spare time. Why did I go down this pathway? What were we talking about? I went on a big sidebar about notation, the real numbers and irrational numbers. Okay, well, I have to get back on topic somehow. Where the hell was I? Oh yeah, we just finished doing the properties of exponents. And yeah, I guess we're going to solve a few now. So let's say we have to solve 25 to the power of 3x minus 2 equals 125 to the power of 3x plus 3. Okay, we want to solve this one, which means that we want to figure out what x is in order to make that equation true. Now, going back to these properties, I want to use these properties somehow. The first 5 were kind of basic ones that sort of tell you about how to interact with powers of powers, multiplying powers, distributing and stuff. It's the last 2 though, number 6 and 7, that we're going to use. Now, looking at number 6, I'm thinking number 6 would work nicely here because what we have is variables stuck up in powers. And we'd like something that can get those variables out of powers and onto like a regular kind of line with an equation that can then be solved. But when I look at property 6, I see something that takes variables from powers and puts it into a nice little equation that we can hopefully solve. So the problem that I see though is that you need the base to be the same. It has to be the same base, otherwise you can't apply that rule. So that's what we have to do next. We have to find out a way to make the base be the same. Okay, so right now we have 25 to the 3x minus 2 being equal to 125 to the 3x plus 3. We would want those to be the same base. Now, what is the number that I want to use if I'm going to try to make those the same base somehow? 5, thanks, Stephen. So 25 is 5 squared. And 125 is 5 cubed. That is much more helpful to me, because now I look at that and I see the same base, and now I'm going to be able to apply that law and not make a mistake doing it. But before I apply that law, what I also see is something that requires law 2. In here I have a power and then a power outside of it. And what do you do when you see that? You multiply the powers. Likewise on this side, 3 times 3x plus 3. So distributing that 2 into the brackets, it's 5 to the power of 6x minus 4. Distributing the 3 into the brackets, I'm going to get 9x plus 9. And now it's set up just how I wanted to have the same base here. So what I can say then is that the powers must be the same. So bringing the 9x across, 6 minus 9 is going to be minus 3. Bringing the 4 across, so I have minus 3x is equal to 13. So x is negative 13 over 3. And the equation is solved. Okay. Did you do stuff like this in school as well? Excellent. Okay. I can keep moving at a decent pace then. So not exactly this. I think so. Okay, I won't skip any examples then. I'll do all the examples I was going to do. Okay. How about another one? Let's say we have to solve 9x squared equals 3 to the power of 3x minus 1. Never solved x, you just simplify. Okay. Now you're not far off then. It's on the same line, so it should be fine. Just a little bit extra. Okay, so again, I'm looking at those two bases thinking I'd like to do something the same, a little bit similar to what I did before, but the bases need to be the same. So this time I'm thinking base 3 looks nice, because then I will have a 3 as the base on the right, and I can just leave this 3 over here on the left and leave the 3 as the base on the right. So again, you have to multiply those powers. It's going to be 3 to the power of 18x squared is equal to 3 to the power of 3x minus 1, meaning that 18x squared is equal to 3x minus 1, and now we need to solve a quadratic equation. A more awkward quadratic equation here. You need numbers that multiply to make positive 18 and add to make negative 3. Numbers multiplying to make positive 18 and adding to make negative 3. I think 6 and 3 do it, don't they? Minus 6x plus 3x plus 1. That won't work. What have I done wrong here? Something's wrong. Oh, I wrote down the wrong sign, didn't I? So I wrote down a positive 1. It's just x squared, not 9x squared. Whoops, what did I do? Oh, you're right, yeah. It was just x squared, not 9x squared. So, yeah, I almost made the question harder than it needed to be. At some point, I must have just saw 9x squared in my head up here and then put the 9 above because of that 9 there. That is a mistake. So I will go back. All this is going to go then. Kind of a coincidence, it looked like it was going to factor even though I made a mistake, so that was lucky. So then this is 3 to the power of 2x squared. So then this is 2x squared is equal to 3x minus 1. And bring in the 3x and the 1 across. Okay, I want numbers that multiply to make 2 and add to make negative 3. This time it sounds like plus 3 and negative 1. No, that's not right. Multiply to make 2. Minus 2 and minus 1, I think. I don't know where I was getting the other one from. Yeah, that's better. And now I can factor by grouping. So 2x times x plus 1. No, times x minus 1. Starting to make more mistakes than usual now, so I think we'll take a break soon. And then factoring out the x minus 1. And then solving. We get these two solutions. Okay. Any questions here? Okay. So I'll do one more example before we take a break, because after this then I'm going to talk about the base e a little bit, e to the x and things like this. Let's say our example then is to solve 25 squared equals x plus 1 to the power of 4. Okay. This one is a little different because the variable that I'm trying to solve is not in a power this time, it's down in one of the bases. So if we roll back up to look at the rules that we have, the 7th one is the one that helps us with that. It says, see these bases here, A and B, it lets us just kind of equate them, provided that the powers up here are the same. So that's something that we have to watch out for. So let's roll down and see. In order to equate the 25 and the x plus 1, we needed the powers on top to be the same. So let's see what we can do here. 25 squared is equal to x plus 1 to the 4. Before we can use that 7 property, we want that and that to be the same. Now, the easiest way that I can see to make this happen is to change that 25 to a 5 squared. And by changing that to a 5 squared, I can use that property that says I can multiply, when I have a power of a power, I multiply them. So it's going to be 5 to the power of 4 equals x plus 1 to the power of 4. And then 5 is equal to x plus 1. So x equals 4. And this one is solved as well. So those are just some examples to demonstrate kind of the point of some of those last properties of exponents, why you would do them. And you're going to see some examples like that in your quiz this weekend and maybe in the final as well. And when we do logs, you'll have even more tools at your disposal. You'll notice that with some of these examples, you need it to work out just right in order for things to work. Like you need, like what, for example, what if that wasn't 25 squared? What if that was 24 squared? And I couldn't say that 25 is 5 squared, and oh, look, magic, we have 4 as the power on the right and on the left, so we can keep going. We're in a bit of trouble if that's 24 squared, or if it was just 24. Logs are your friends in those cases. You're actually able to use logarithms to solve in those more awkward cases. And we'll be doing that today as well. We're just going to be talking a little bit about the special number e, that special base. You might see e to the x a lot. We'll talk about that a little bit. And we're going to move on to logs shortly after that. Okay, I'm going to take a little break. I think I'm starting to make mistakes. Maybe it's the jet lag, or maybe I'm just tired today. So I'm going to take a little break and go outside, and hopefully I won't make any mistakes when we come back. So what I'm going to say is break until, and there are not two L's in until, so I'm definitely tired. Um, let's say 11:25. That's just over 10 minutes. So make sure that you're back in time if you leave to get a snack or something. Okay, and if you have any questions between now and then, just pop it in the chat and I'll deal with it once I come back. Okay. Hey everyone. Okay, we'll get started again. So yeah, I see you missed the question about question 6. Thanks, Evan. Yeah, that's the answer. You get full marks for question 6. That's the one about the one that involved the long division, because my mistake made it a little bit harder. Okay, so I think what I'll do is run back to the screen share over here, talk about base E, because I kind of have a lot of the important stuff written down anyway. Okay, so okay, good, there it is. The important thing to remember when you see something like e to the x, or you think about base E, is that E is just a number. It was always kind of seen as something a little bit strange or odd, or just this weird thing that's caught up in the exponential function section, and people keep talking about e to the x, whatever E is. All you have to do is think of E as a number, any other number. It follows the same rules as 2 to the x, 3 to the x, 4 to the x would. It's a number, it's Euler's number. Euler was a famous mathematician. And it's approximately 2.718281828459 ... It goes on forever and ever and ever, never repeating. Like, for example, like pi. Pi also doesn't repeat. 3.14159. I forget the rest of them. Actually, nobody knows all of them because there is an infinite amount of them. But it's an irrational number, never repeating, going on forever. And how this specific irrational number is chosen, or how it's found, like, why not some other one where instead of 2.718, why not 2.818281? Well, there's a few different places where this number has shown up in nature, or in certain calculations in finance, or everywhere else, that it appears to be an important number in math and in science in general. So here are some of the things that can be found in. If you look at the expression 1 + 1 over n to the power of n, and you let n get really, 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 really big. So if you went to your calculator and typed in 1 + 1 over, let's say, 999,999, all to the power of 999,999, you would get a number that gets close to E. And the bigger you take that number, you go to a million, 9 billion, trillion, gazillion instead of n, you're going to get closer and closer and closer to that E value that I have there, 2.718, and so on. So it's a number that expression approaches. Another way that you can describe it is in the second bullet there, 1 + 1 over 1 + 1 over 1 times 2 + 1 over 1 times 2 times 3 + 1 over 1 times 2 times 3 times 4. And the further on you go with that series, the closer and closer you get to E again. Something interesting about it is that it is the base of an exponential function. It's the base that you might replace with a. If you replace 2.7182 with a there, so that what we're talking about is e to the x. An interesting thing about that, as far as calculus would be concerned, would be that that is the base of the exponential for which the slope of the tangent line is equal to 1. So if I come back here for a second, just to demonstrate what I mean by that, on the screen here. Just takes a minute to start the broadcast on the iPad. So what we're talking about was base E here. Whoops. So you remember we talked about 2 to the x. If 2 to the x looks something like that, then 2.7 to the power of x, or as we're now thinking of it as e to the x, since e is a little bigger than 2, it will be a little lower down here, and it will increase a little faster here. Okay, so, but what we're talking about a second ago about the slope of it is about this here. If we draw e to the x like this, if this is y equals e to the x, then the tangent line at the y-intercept would be this one here. What that third bullet was saying is that the tangent line here, it has slope 1, which is kind of an interesting feature. That wouldn't happen for any other exponential function, because as we talked about, for numbers bigger than e, like 3 to the x, 4 to the x, 5 to the x, it would be a slope bigger than 1. For numbers smaller than e, like 2 to the power of x, it would be a slope smaller than 1. E is, funny enough, that number e is the one that makes the slope equal to 1. So it's kind of strange in that way. You have this irrational number that just makes no sense really when you just look at all the digits. It doesn't repeat or have some kind of pattern that you can see. 2.718, blah, 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 blah. That one, though, if you look at the exponential function for it, that has this lovely, neat slope of 1. A whole number, 1 is probably the most important number. You know what I mean? It's a strange thing, but it happens with e in particular. And something else, you've probably seen this famous equation, e to the I pi plus 1 equals 0. So that is one of the most famous math equations that you'll see, because it contains some of the most important or foundational mathematical objects. 0 is a very important mathematical concept or object. 1 is a very important one. Pi, obviously, a very important number too. E, as I'm trying to convey right now, it's another very important one. And this I here, this I is actually the complex number I, square root of -1. In this course, we're just assuming the complex numbers don't exist, and we're just looking at real numbers only. But as you progress in university, you're going to see more about complex numbers, I, as well. So this is a very important equation, again, by Euler. It actually links all those very, very important numbers in one equation and has been proven true. So it's, again, E shows up in there with the other important numbers. So if you're thinking about what E is, or what's the point of it, think of it as kind of thrown in there with pi, a very, very important irrational number. It shows up in different places in maths. You might be inclined to think of pi to do with circles, but the more you study maths, the more you see it in different places in different areas of math too. E is like that too. Think of it as like pi, irrational number, can't write it as a fraction, tons of digits, the digits never repeat, important number. That's really all you have to kind of remember for E. Some of the other places it shows up, probability. If you see any probability in your studies, you'll see it in the probability density function of the normal distribution, Poisson function, and the exponential distribution as well. If you do any physics, you'll see it in Newton's law of heating and cooling. It's a solution in the differential equations. If you see it in finance, this might not be one you see too much, but if you have an understanding of how compound interest works, where you take interest on your interest, and it depends when you do it. Like for mortgages or for things like this, compound interest is done monthly, but you could have interest compounded weekly or daily or hourly, or even, let's say, compound interest compounded every second, every millisecond. E will show up in the formula for continuous compounding. As you let that time difference of the compounding approach 0 by taking a limit, E shows up. In mathematical models for growth and decay, E shows up if you're thinking about mathematical biology. So it just shows up in lots and lots of places. It's an important one. Might seem kind of random that your professors and stuff and in different places just randomly start doing e to the x whenever they talk about exponential functions, but I think the reason is just to get everybody familiar with it, because you're going to see it a lot more in future math anyway. So just to get a level of comfort working with E and to have an idea of what it is, instead of just using the same old numbers 2 and 3 and stuff, this is an area where E just gets shoved in a lot to practice with. Okay. So that about just sums up exponents. We can do more with exponents once we have logs again. So what we're going to move on to now is logarithms. Any questions about exponents? Feel free to unmute or pop them in the chat right now, because I'm just about to move on, so now would be a good time to ask something before I get stuck into logs. But we're definitely not done talking about exponents, because first thing I'm going to say is the log in the log section is think of logs as the inverse of exponents. Again, logs are a topic that I don't know what it was like for you in school over here, but I felt like my teachers never really, in high school, never really explained what you're doing when you're working with logs. It was you're working away doing math and you're doing your X's and Y's and stuff, and then suddenly there's logs and they're saying log of A times B is log of A plus log of B. Okay, remember that. And I go, okay, and there'd be just this word log everywhere, and you'd have to try and memorize what you can and can't do with this weird word. So I'm going to spend a bit of time trying to make sure that you get where they come from and what they're about, rather than just practicing. And the practice will be left to you, I guess, to work through some of the examples and everything. But okay, let's think of exponents for a second, right? I think everybody is satisfied with me saying that 2 to the power of 3 equals 8. Okay, 2 cubed equals 8. So the exponential function is 2 to the x. And what does that function do? What does this function do? Well, it sends 3 to 8. When we use that function, that 2 to the x, and we take a number 3 and we plug it in, what gets spit out? 8 gets spit out. So if f of x is 2 to the x, then f of 3 is equal to 8. Okay? If a log is the inverse function of an exponential function, it should send 8 back to 3 again. Okay? So a log function should send 8 to 3. Okay? So if we have f of x equals log, our base is 2, right? Because the base is going to match this here. That's the base. What we just said is that it should send 8 back to 3 again. So if my f of x is log to the base 2 of x, then log to the base 2 of 8 should be equal to 3. F of 8 equals 3. Then it's the inverse function of 2 to the x. Now, I was saying that log functions are inverse functions of exponential functions. So how you know which one is which? So if you have 2 to the x, the inverse is log to the base 2. 5 to the x, log to the base 5. 15 to the x, log to the base 15. Those are the corresponding inverse functions. Okay. So, for example, oh yeah, it's already here. So log to the base 2 of x. Any questions so far? Okay, so if you see, for example, how that inverse was made, the best way to answer this is to say that we defined it this way. So going back to exponential functions for a second, let's say we have 2 to the x like this. So this might be 2 to the x, right? If I'm trying to think of this and I'm looking at this and thinking, Okay, that appears to pass the horizontal line test. Anywhere I draw a horizontal line, it cuts it only once. I can look at this and say an inverse surely exists. So there is some function that, if 3 is sent to 8, then 8 is sent to 3. I can even draw it, right? I could draw the inverse of it if I just draw this a little bit better so that I can do it. If this here is 2 to the x, and that there is going through 1, then this here is going to be the log function, because it's going to be the same thing except reflected through the line y equals x. So this here gets reflected through, and that should be going through at 1 as well. Yes, the inverse will always be log with whatever the original base was. If it was 2 to the x, it's log to the base 2. 7 to the x, log to the base 7. The base is going to be the same for it to be the inverse. Now, the question is, what do we call this function? This is, the inverse exists, and if I draw it, what I'm doing is choosing to call it something. I'm going to just, you can think of it as making up a word log, right? Call it log to the base 2. If it was 3 to the power of x, then it would look more like that, right? And the inverse would look more like this. Well, then I'll call that one log to the base 3 of x. And then with the x at the end. Yes, exactly, with the x at the end. So call it log to the base 2 of x. So it's kind of like, we know that it makes sense. We can draw it if we want. We don't really have notation for this, because if we look at 2 to the x, you might say, what might first pop to your head is, what about x to the 2? Oh no, that's x squared. That's something different. So that's nothing to do with exponential functions in that way. We'll make up a word and we'll call it logarithms. And we'll say that here, in the first case here, let me get rid of this. Whoops, got rid of too much there. This is only for exponential functions. They're the only ones where log is the inverse. So think of exponential functions and logarithms as cousins somehow, where they're related in that, like, this one does it and the log function undoes what the exponential function did. So for example, for 2 to the x, let's say what happens to 1 here? Well, 2 to the power of 2 is 2. So what should the log function do? So 2 to the x, right? 2 to the 1 is equal to 2, so 1 gets sent to 2. The log function should take 2 and send it back to 1 again. So this graph that we have here, 2 is over here. Okay, my graph isn't very good because it should go back to 1, but the log function will send it back. So log to the base 2 of 2 equals 1. Okay, so you can think of them as related in that way. And when you look at a log expression, when you see a log expression and want to evaluate or get a sense for how big it is, or small, I guess, depending on it. Big, man, my grammar's all over the place today. I'm really tired. How big it is. Then, okay, let's say, for example, we have log to the base 3 of 27. So just going back up here for a second, we talked about how if 2 cubed is 8, then what we should have is log to the base 2 of 8 equals 3. So 2 cubed is 8. So 2 to the power of x is sending 3 to 8. Log to the base 2 should send 8 back to 3 again. Okay? So let's just look at this right side here. If I'm thinking about what that does, for an exponential function, if I'm plugging in 3 into it, I'm thinking, okay, 2 cubed what is it when I raise the number to the power of 3? What do I get? I get 8. But when I'm looking at the log part of it, and I'm thinking, what's log to the base 2 of 8? What I'm thinking is log to the base 2 of 8. What power did I have to put on 2 to make 8? And 3 is the answer. So when I go back here, when I'm looking at this, I'm thinking, think about this. What power needs to be placed on the 3 to make 27? That's what runs through my head when I look at an expression like that. I say, what do I have to raise 3 to the power of to make 27? Well, 3 cubed is 27, so the answer is 3. Okay. If I go back to this one here, for example, log to the base 2 of 8, I'm thinking 2 to the power of what makes 8? When I see log to the base 2 of 8, 2 cubed makes 8, so the answer is 3. Now, it's not always going to be nice, right? Because sometimes the power isn't nice. If I see log to the base 4 of 17, 4 to the power of what makes 17? It's not very nice because there is no nice whole number that makes 17 for you. But if you think about the powers of 4, 4 to the 1 is 4, 4 to the 2 is 16, 4 cubed is 64. So 17 is between 16 and 64. It's a lot closer to 16 than it is to 64. So I'm going to go ahead and guess that this is something like I was going to say 2.1, but I think that might not be small enough. I'm going to say 2.08, right? I don't care what it is, but this is the sort of thing you're going to try and think of. Say, if I want to get a sense for how big that is, maybe it's about 2.8, because I'm guessing that 4 to the power of 2.8 is close to 17. Now, it could be totally wrong. So I'm just going to search it. Log to the base 4 of 17. Let's see what we get. So what it actually is, according to the internet, is 2.04373, yada, 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 and so on. It doesn't really matter. I only wanted to have a sense for how big it was. Is it close to 2? Is it close to 50? Is it 1? So, but to understand what the log function does and how it's kind of the reverse of the exponential function, what I'm doing to just get a sense for how big a number is if there's a log involved is bring it back to exponents in my head a little bit and say, if I was trying to figure out what power I have to put on 4 to get 17, then I'm thinking it must be close to 2, because 4 to the power 2 makes 16, so it can't be much bigger than 2 to make 17. So this kind of understanding just helps you have a sense of what the log function is and what it does and how big the numbers are that you're talking. A little more than just treating it as this random word called log, and I have some rules that I have to learn. I think it's nicer to be able to relate it to the exponents a little bit more and have that understanding of where it comes from. So, okay, it was actually not 2.08, but it was close enough for my purposes of just wondering, roughly what ballpark are we in? So the main thing here to take away, I think, is that if you have an exponential function written like this, y is equal to b to the power of x, then that is the same thing as saying log to the base b. Okay, so maybe I'm going to let you think about this for a second before I write it down. The one thing that I had to make sure was that I'm using the same base for both of them. The base for the exponential function on the left side that I'm thinking of, that's the thing that is supporting the power, right? Is the base there. And the base for the log function is the subscript that's written just below the g. Those are the things that must be the same if they're going to be inverses of each other. So now this exponential function on the left side here, that is taking x, and the answer that you get in the end, whatever you plug in for x, you get y back. The exponential function for log is going to work in the other way. You're not going to plug in x, you're going to be like plugging in y and getting an x back. So if I'm looking at a bunch of examples here, let's say I have 16 equals 4 squared. That's the same thing as log to the base 4 of 16 equals 2, because 4 squared is 16. Let's say we have 25 is 5 squared. My base is 5. The kind of answer on the other side, the thing that came out was 25, and the thing that I plugged into the function on the other side was the 2. And so on. So that's really the main thing to remember, is that logs and exponents are related in this way, and they're the inverses of one another. Okay. Are there any questions so far? Can I get everybody to tell me from 1 to 5 how good you're feeling about this? 1 is terrible, 5 is fine, 4 is, you know. Very good, Lewis. 4.2. I like the specific answers. Okay, that's good. A lot of people feel pretty good. Very good, very good. Stephen, was there anything that kind of passed you by in all this that makes you vote a little lower than everybody else, I wonder? Any questions in particular? Not really, just unfamiliarity kind of. Okay. Yeah, I'll be posting this video as well, and I will. You can find the explanations in the textbook as well. You can find lots of questions to practice in the textbook. So hopefully, some practice will help. And if there's if you're thinking about it afterwards and you're going, well, actually, back when he said this, it didn't really make sense. Just send me an email, and I'm happy to answer any questions as well by email. And we can make an appointment if need be too. It doesn't always have to be email answers. If something's a little awkward to explain by email, you're always welcome to make an appointment. Speaking of, don't forget that this week for your academic coaching, it is just individual little check-in sessions, 10 minutes each. So if this is news to you, just check your emails, because I emailed you last, I want to say Friday, but the days have all kind of morphed into one since I traveled now and stayed up a day and a half trying to beat jet lag. Check your email and just see which time you're down for, and make sure you join exactly on time, because I've put our little check-in sessions like exactly back to back, just to help with my own timekeeping and time management for it too. So just make sure that you join exactly on time, and yeah, don't join early because I might be just still chatting with somebody, and don't join late either, because it's going to affect the time that we have too. So all I really want to talk about is how you're doing with the course, and we can do to support you a bit more as the academic coaches, and whatever else might come up. So don't forget about that. They start at, for the first person for me today, starts at sorry, the time difference, 1:30. Yeah. So yeah, half an hour after class ends is when they're starting. So if you're the first one, just make sure you're on time. And be prepared to have your cameras on. Especially when we're in a one-on-one meeting, it's I want to see the person that I'm talking to, and it's kind of a matter of professional etiquette and respect as well. You never really attend a meeting and just sort of leave the camera off. It's something you're going to have to get used to in professional spaces and in university as well. Okay, where were we? So we talked about logs, the introduction. People feel okay. I should mention a few other things, okay? So there's some special notation to be aware of. If you have a base 10, it's just log of x. So that is that you don't write log to the base 10 of x. I guess base 10 is considered an important and special base in math because it's how our math is built, right? We count to 10 and then we reset with 11, 12. Then we get to 100 and we reset and we go to 1, 2. So base 10, 10 squared, 10 cubed, they're kind of the key numbers where our counting kind of resets and everything. So, well, except for in timekeeping, it's like 60 there, isn't it? So for 1 hour, you do 60 and then hour 2 and then another 60 minutes. But in general, in most of our calculations, base 10 is the important number. So for the longest time, if you just see log written anywhere without the base specified, you can assume it's base 10. Yeah, you can write anything above 10. So you go back to log to the base 11, log to the base 12. So for example, if you were writing them, you would have log to the base 8 of x, log to the base 9 of x. You would then just call it log of x, log to the base 11 of x. It's just a stupid convention, but you're going to see it in books and on the internet all the time, and it's just something to be aware of, really. If you were doing a calculation and you wrote log to the base 10 of x on me, I don't think I'd take any marks. I'd probably just circle it and be like, drop the 10, but it's just a convention thing, really. It's not a huge deal. What else? Oh yeah, log for base e. The notation is not log to the base e of x. It's ln of x. And you read it as the natural log of x. So you read it as the natural log. Again, e gets special rules because it's such a special number. Instead of log to the base e, it's ln of x. And I think I've seen in the past, people must have been paying attention or not really paying attention in school. So they'd see this thing written down and they probably weren't listening to the teacher or whatever, but that first letter here is an L, not an I. I've seen people call it IN and write it like an I, which is kind of funny. But yeah, it's log natural log. So that's something just to watch out for as well. It has a special notation. So the sketch of it, I think I did this already. I kind of talked about it being the inverse. Log functions are going to look like this. That could be, without putting any notches on the x-axis and y-axis, you can see exactly how steep that is. That all you know if I'm looking at that is that it is a log function. You don't really know which one or anything like that. So let's just call this one log. Let's just call it log of x, log to the base 10, for example. Some of the features that you'll notice on this one is that the domain is from 0 to infinity. You'll notice that you don't see that graph drawn to the left of the y-axis, so there's no negative x values in there. Just like how the exponential function never touched the x-axis, when you transform that through the line y equals x, this log function is never going to touch the y-axis. It's just going to run alongside it, never touching it. So 0 is not included in the domain, but the domain is everything from 0 onwards, not including 0. The range is anything at all, minus infinity to infinity. It looks like it's starting to level out a bit, but it never actually stops. It'll always go higher and higher and higher. It just takes a very, very long time to get there. But the domain and the range are both, the range is from negative infinity to infinity. You have a y-intercept. No matter what the log function is, the y-intercept is going to be, I'm writing it wrong here, 1, 0. No, I'm being stupid. There's no y-intercept. It's the x-intercept I'm trying to say to you. Y-intercept is none. X-intercept is 1, 0. I'm not really going to mention the asymptotes on the page here. I think they're in the book, but we didn't cover asymptotes in this course. But The vertical asymptote is the y-axis, which is the line x equals 0, and there is no horizontal asymptote. So even though it looks like it's starting to level off, it won't actually flatten out to an asymptote. It'll just keep rising, just slower and slower and slower, but it does keep rising. Okay. So that's what a log function looks like on the graph. And I think we talked a little bit about this as well, but some examples as a reminder. I end up kind of touching on some of this stuff as I'm trying to describe how it's the inverse. But just to recap it again, log to the base 3 of 27. When I read that, what goes through my mind is 3 to the power of what makes 27? 3 cubed is 27, so the answer is 3. When I look at, okay, here's one that's in a funnier kind of order here. Don't forget the way you have to think of this. This looks like a trick question here. When I read this, I have to think of 25 to the power of what makes 5. Not 5 to the power of what makes 25. It's 25 to the power of what makes 5. So can anyone write it down in the chat if you know what it is? Half. Exactly. -2. I see where you're getting that from, because you're thinking of the half as 2 to the -1, I think is maybe what you were, because you're thinking of the half as being kind of reversed. And we sort of talked about that when we were talking about the graphs of exponential functions. Yeah, it'll be a half though, because like you're probably thinking, well, 25 to 5, that must be the square root. But yeah, it's 25 to the power of 1/2. Yeah, I see where you got that from. And so you have to watch out. Sometimes it can be a little tricky. And just one more simple one to renew everyone's confidence here before we move on, because it's kind of a tricky one. Again, I look at this and I go, 4 to the power of what makes 16? 4 squared is 16. So that's what I'm thinking about when I'm looking at a log expression and saying, what is the what's the answer here? Some other things that I'll also mention here is, let's say the question is to write in exponential form. I think I've taken some of these from the textbook questions actually. So let's say I have log to the power of 1000 equals 3. What is the exponential form for that? Anyone write it in the chat? You can use this little symbol here as power. Whoops, in the chat. That little symbol there is power. 2 cubed equals 8 or something. What I want you to do is change that into the corresponding log notation. Or sorry, you're given the log notation, change it into the corresponding exponential notation. Anyone write it? Yes, Andreas. 10 to the 3 equals 1000. So, very good, Stephen. So, I feel like when I was taught logs first, this formula here, you can almost treat that as a formula, and you can say, you can kind of look at this and say that this is log to the base 10 of 1000 equals 3. So if I change this to the exponential notation, my b is here, so that's where my 10 is going to be. My 1000 is going to be in here in the y, and the 3 is going to be up here in the x. I'm just not a huge fan of relying on a formula for an understanding of the relationship between logs and exponents. But if this is something that you prefer, you like to have formulas put in the box for situations, that you can think of that as a formula, that where the thing comes from. But I think in practice, for your own understanding, it's better to have a sense of what the log function does in terms of the exponential function, like how I've been talking for the last half an hour. kind of avoiding just transcribing a formula and saying, here's my b, here's my y, and here's my thing, and oh, that's what came out. And I don't, 10 cubed is 1,000. That should be kind of coming naturally from log to the 10, or sorry, log of 1,000 equals 3. Let's say another one. Let's say we have, let's kind of mix up some numbers and letters. Log to the base 4 of c equals d. If I wanted to write that in exponential form, what does that mean in log? What does that mean? Anyone write down what this one would be? D to the 4 equals c. Anyone have something different? So, Stephen, double check which one is the base in your situation there. What's the base when I say log to the base 4 of c? Yeah. There you go. 4 to the d equals c. Yeah, just something to watch for there. And probably just a typo for you there, but 4 to the d equals c is what you want there. Okay. And you can also go the other way. So let's say I want to say write in logarithmic form, and I have 2 to the 4 equals 16. So I do end up talking about this when I describe what a log function is. So now what we're trying to do is log to the base something of something equals something. So what's the base, what's the first something, and what's the second something? A little more awkward to write in the chat. In this case, when I said 2 to the power 4, 16, 2 is my base. So it's log to the base 2. The exponential function sent 4 to 16. So my log function is going to send 16 back to 4. And when I read it, I always read a log function as like 2 to the power of 4 makes 16 in that way. Okay. Those lines probably aren't helpful actually, so I'm going to take them away. And let's say I have 10 to the power of m equals n. Can someone write in the chat for me how I'd write this in log form? Here we go. Or unmute if it's easier just to speak it out if you want. Log of n equals m. Yep, that's it. So yeah, the one thing to remember, Jamal, is that we have that pointless rule that if the base is 10, you don't need to write the base. So log of n equals m. But yeah, full marks, you get the idea. Okay. Any questions here? You're good about logs so far, I hope. So just like with exponents, we had rules, we had a to the x times a to the y equals a to the x plus y, and ab to the x is a to the x, b to the x, and so on. There also are corresponding log rules. And if you think hard enough, you can see which exponent rule has which kind of log rule as its cousin. They're a little bit hard to spot, and I'm not going to, talk too much about how you can see which are the ones that are related to one another. But it's something that you could spend time doing if you wanted. So properties of logs, I'm just going to call them here log laws, is probably what I'll refer to them for shorthand. I'm gonna just run through them. They're also in the book in a box in the book to review these, but I'm going to go through them here. So if B, capital M, and capital N are positive, B is not 1, P and X are real numbers, then each of these rules are going to always be true for any log function with that base. So log to the base b of 1, maybe someone can tell me, based on your understanding of logs now and how you're able to kind of flip it over in your mind to exponential functions, what should log to the base b of 1 be? In this case, I'm thinking no matter what the base is b to the power of what makes 1? Anyone write it down? B to the power of 1 makes 1. Is this what you're saying? So it's 5 to the power of 1. Is that equal to 1? Or 6 to the power of 1. Is that 1 as well? Yes, 0, yeah. If I'm thinking, what power do I have to put to make 1? Oh, sorry, maybe I said it wrong, did I? I'm tired today and I'm speaking kind of weird, so maybe I said the wrong thing. B to the power of 0 would make 1. So no matter what the base is, so yeah, log to the base b of 1 would be 0, no matter what the base is. How about this one? Log to the base b of b. So now I'm thinking b to the power of what is equal to b? Yes, b to the power of 1 is what's b. So that's always going to be a 1. So if you see, for example, log to the base 5 of 5, 5 to the power of what makes 5? 5 to the power of 1 makes 5. You can always just replace that with 1 in some equation that you're solving. So some of these rules are ones that I think you would expect anyway. Log to the base b of b to the power of x. Again, you can kind of use your understanding. B to the power of what makes b to the power of x? B to the power of x makes b to the power of x. This here is going to have to be an x. And another way to kind of understand it is to think, well, a log function and an exponent function are the opposite of one another, right? So if I have a function like this, right? Let's say it's b to the power of x. Then x is being sent to who knows what. Let's call it k, capital K. The log function should undo that and send k back to x again. So if you have b to the x and then you take log to the base b of it, you can kind of think of the log to the base b and the base here itself sort of cancelling one another, and everything just gets back to where it started. You started with x, and then you got whatever b to the power of x would be. But whatever that b to the power of x is, I'm just calling it k for something different. That log to the base b of k is going to go back to x again. So log to the base b undoes what the base of b did because they're inverse functions. So there's kind of multiple ways to think about these. I'm just going to make some space here again. And likewise, the other way around. If we have b to the power of log to the base b of x, well, we started with x. Log to the base b of x changed x into something unknown. And b to the power of that unknown something is going to move it back to x again. So again, it's a little like that log to the base b and the power of b sort of undo one another. First you take x and you do that log to the base b to it and you get something. Then you put that something in the power of b and you go back to x again. So it's like the inverse action is kind of undoing what you just did. Okay. Here's some important ones that you're going to use a lot depending on how far I get today. They might be in your quiz this week, but if I don't get enough done today, next week, no, I should get them done this week. Okay, let's say we have what are we doing? We're doing log law, sorry. So log to the base b of m times n, log to the base b of m plus log to the base b of n. This is like the inverse of the one of the exponent laws. Oh, m and n are just two variables. So another way to think of it would be like a times b. So you could have log to the base b of a capital B, a and b. I think I decided to use a and b because the base, or m and n, because the base of b is a lowercase b, and I didn't want to use an uppercase b, so I was looking for two other letters just to use for this part. M and n are just positive numbers. Okay. So that's a log law that you can use that will be very useful in some calculus problems. Like if you're trying to take a derivative of a very complicated log function, you can use a law like that one and the next one you're about to see to turn that complicated function into a sum of simple functions. And the derivative of those simple functions is very easy compared to a derivative of a complicated function. So these ones you definitely want to get familiar with. Rule number 6, log to the base b of m over n. That's log to the base b of m minus log to the base b of n. So that one is a subtraction, and the next very important one is this one here. Does anybody remember the rule that I'm about to write down? I'm just wondering how familiar you are with logs. Can anyone type in the chat if you know what's coming? Nobody? Or it just is awkward to type is the question. Maybe just give me a yes if you know what the log law for this one is. B of n. No, it won't be n. Well, that won't be it. Is this new to a lot of people? Is new. Oh, you think you know, Stephen? Okay, if you've seen a rule about power inside in the log like that, you think you know, but you're not certain. You don't want to bet money on it, kind of. But yeah, it's that the p can come down in front. That power. Okay, that's something that you can use to simplify log expressions as well. You do remember. Very good, very good. Yeah. No problem. I just thought you were very excited for a minute. Now you've ruined my happiness a little bit that you're not that excited about logs as I thought you were. It's a hard topic to be excited about. I can forgive you. Okay, so yeah, bringing down the power is something you can do. Now these all seem kind of arbitrary, but you're going to find these useful when you move on to calculus to do complicated calculus problems. I know most of you have probably touched on calculus a bit in school already, but from my understanding of it, the proper limit definition of it wasn't taught very well. You don't really go too far in to do some of the more complicated functions, so you're going to have to deal with hard kind of functions. Anyway, and one last log law that you're going to use from time to time to solve log equations. If you have the same base like this, log to the base b on both sides, and on the left side you have one thing in the brackets and on the right side you have the other, well, that is true if and only if those two things inside are equal. And the key thing you have to be aware of before you can just kind of drop the logs and work out what's inside is make sure that those bases are the same. That's the important thing here. So those are the log laws that you need to know. You definitely want to be 100% solid on all of them. The first 4, even though I'm writing them down as log laws, I think they're things that you can figure out from having an understanding of what a log function is. Because when I write down the first half, log to the base b of 1, you should be going b to the power of what makes 1? Well, it has to be 0. B to the second one, b to the power of what makes b? Well, it must be 1, because b to the 1 is equal to b, and so on. So you're able to kind of have a sense of what those ones are. These 3 here, 5, 6, and 7, those get used a lot in a certain type of question that I'm trying to remember. I don't. It'll definitely be on your final. It'll either be on this week's quiz or next week's. Again, I didn't put more questions on your quiz, so it's if I don't get to it this week, I wanted to stop at 5 or 6 questions. So if I don't get to it on this week's quiz, it'll be on next week's. But it'll be like expanding log functions and using these log laws will be the topic of the question. So you'll definitely want to be very, very comfortable with those laws 5, 6, and 7. Okay, so let's use some of these laws that we just have to evaluate the following. So 1, log to the base 3 of 54 plus log to the base 3 of 3 over 2. Okay. My first instinct here would be to look at this and say, okay, let's do it piece by piece and start with the first bit. First bit is log to the base 3 of 54. So I immediately say in my head, 3 to the power what makes 54? 3 squared is 9, 3 cubed is 27, 3 to the power 4 is 81. So it's somewhere halfway between 27 and 81. Maybe not halfway, I'm not sure exactly where. So that looks like a number between 3 and 4, some horrible decimal number that I can't do. I don't know. I can't do anything with that. Looking at log to the base 3 of 3 over 2. 3 to the power of, yeah, it's going to be 3 point something. Definitely, Lewis, 3 point something. For the second one, I'm going 3 to the power of what makes 3 over 2. So 3 over 2 is 1.5. Maybe the square root of 3. No, because that's 1.7. The cube root might be too far. Maybe it's some sort of a fraction between 1/2 and 1/3. Or maybe between 1/2 and 1/4. I don't know. I can't really do it, right? But now I have more tools in my toolbox than just saying, oh, 3 to the power what makes 54. What I can do is go back up and look at some of these laws. Now, the one that's standing out to me is law number 5. Because that one, and I'm looking at the right side of it, log to the base b of m plus log to the base b of n. If I have the same base, which I do here and here, by rule number 5, I can say that that is going to be log to the base 3 of 54 multiplied by 3 over 2. And let me just make a note here. This is by rule 5. Wait, I told you I was going to call them laws, didn't I? By law number 5. By log law 5. So that's something I can do. Just going back to number 5 here. If you have, here is where my 3 was, here is where this was like 54, and this was 3 over 2. And going backwards, doing it the other way around, I have changed this to log to the base 3 of 54 times 3 over 2. Okay. I think the answer is 4. Let's see. I think you might be right. Let's see what we get. So what happens? Let's multiply these and see what we get. So 2 into 54 is 27, and 3 times 27 is 81. So if you multiply 54 by 3 over 2, you get 81. And yeah, I think you're right, Jamal, because now my question is again, 3 to the power of what? So I'm just going to write in brackets here. Now I go back to thinking 3 to the power of what makes 54? Oops, that's not a bracket. That is a colon thing. And yes, the answer is 54. No. I'm tired. The answer is 4. Okay. So that's one way that we could use the log laws to simplify a little bit. What if I did another example? Let's say we have to evaluate log to the power of 5 of the 6th root of 125. So we're going to try and evaluate log to the base 5 of the 6th root of 125. Again, I think 5 to the power of what makes this thing, but the 6th root of 125, I haven't got a clue what that would be. That could be anything. But there's a law that's going to help. So just rolling back up here, can anyone tell me which law I want to apply? 1 of 5, 6, or 7? Just pop the number in the chat. Applying one of these laws helps. Law 7 will help. That's right, Stephen. Law 7 is the one. But it looks a bit strange, doesn't it? It doesn't look like it'll immediately apply, but there's something that I can do to make it work. Can anybody say what I should do first before I apply law 7? Change the root to exponent. Yeah, you're right, Stephen. Lewis, I think you wrote the wrong number, but I think I see what you were doing with the 6. You were writing it as over 6, which is what you want to do. So what we have to remember is that, for example, the square root is like 2 to the power of half. The cubed root is like 2 to the power of 1/3. The 7th root of 2 would be like 2 to the power of 1/7. So just taking this away here, this doesn't really need to be here. This means that the 6th root of 125 is going to be 125 to the power of 1/6. And now law 7 works. I can move that power that I have down in front. This was by law 7. And yeah, now I can evaluate this thing here. So when I look at that thing in here, now what's going through my head again is 5 to the power of what makes 125? 5 cubed is the power of 125. So that's going to be a 3. And then finally, 1/6 multiplied by 3 is 3/6, which is 1/2. Yes, exactly, 1/2, Jamal. So the log laws can help to simplify things that are looking complicated. And here's an example of expanding logarithms. Go ahead, Lewis.
To change something, if for example I turn like the 125 into 5 to the power of 3, and then simplify it with the root of 6, and then I go to multiply. Does it matter?
Oh, right. So you were thinking if. Oh yeah, I see what you mean. Yeah. So yeah, no, that's totally fine. That's all totally fine as well. So going back to the 6th root, like you were saying, the 6th root of 125 here, you can say that that is the 6th root of 5 cubed. So you could say that it is 5 to the power of 3/6 which is 5 to the power of 1 over 2. And then finally bring down the half. And you can say log to the base 5 of 5 equals 1. And you get the same answer of a half that we got above. Yeah, there's different routes to go sometimes. You can kind of change the order around and do some little bit of simplification first instead of later. So yeah, that's totally fine as well. Totally correct. Okay. Okay, so an important topic, and I think this will be the last one that I do. Expanding logarithms. So what I mean when I say expanding is to apply the log laws as much as possible to like separate everything out as much as possible. So the best way to describe it is with an example. And this might seem like an arbitrary sequence of operations just because you can, but I'll talk a little bit about why you might do this as well. Let's say I want to expand log to the base 3 of x minus 3 cubed times x to the 4 divided by 3 times x minus 1 by the 5th root of x minus 2. Okay, so when I say expand this, what I mean is apply all the log laws as much as possible and get that into a whole bunch of log terms that look simple, a whole bunch of simple looking log terms instead of one super complicated looking term. And the reason for it, again, I'm always thinking of calculus in mind when I'm talking about stuff. If you're asked to find the derivative of that, that is horrible. That's going to be awful amounts of calculation involving a rule for taking derivatives of logs. You're going to have quotient rules. You're going to have chain rules. It's going to be horrible, doable but horrible. Whereas if you do the steps I'm about to show you, that derivative becomes easy. It's a derivative of a bunch of easy things that will be very, very easy to do. So, okay, the first law I see working here is I see this in a form of a log of a over b. Now, the a and b are still kind of complicated. So I'm looking at this first as a log of a over b, and I'm going to go back up and use law number 6, that one where I have a fraction inside my log term. I change that into 2 log terms and do a subtraction. That's going to be the first thing that I apply here. So it's going to be log to the base 3 of x minus 3 cubed times x to the 4 minus log to the base 3 of 3 times x minus 1 times the 5th root of x minus 2. Yeah. So one really complicated looking log term now turned into 2 less complicated looking log terms, but we're going to keep going and split this up even more. What I'm seeing now is I'm seeing 2 terms that both look a little bit like this, like log of a times b. I'm seeing an a times b here, and I'm seeing actually 3 of them in here, but the rule can be used twice to separate them all out with addition. So I'm looking at all that and seeing multiplication inside the log, and the rule is that you can separate those out into separate log terms with addition. So going back up to law number 5, addition is going to be used to separate these ones out. And here we go. So this is going to start getting kind of big, and better start writing a little bit smaller. I better open a bracket here because the addition, that minus sign is going to apply to all the terms that come out with this addition, not just the first term. So I'll just open a bracket there to be accurate. And just about enough room, almost not enough. Okay. Some things I'm noting here is that I have a bunch of powers that I can move down. So I think that's what we're going to do next. We're also going to, you know what, before I move the powers down, I'm going to do that all in the one step. This here can be simplified. The minus sign can be distributed, and this power of 5 here, that can be changed to, sorry, that fifth root can be changed to a power of 1/5. So I'm going to do all those steps first, just to tidy it up a little bit before I continue with the log laws, okay? So again, I might just try to write a little smaller in this step. Make sure that it all fits. These are going to wait, and then the next term I'm going to do all the power laws at the same time. The minus sign I'm going to start distributing, so I'm going to drop the bracket. What is log to the base 3 of 3? So I'm thinking 3 to the power of what makes 3? 3 to the power of 1 makes 3. Okay. My minus sign is distributing onto this. Not much happening here. And a minus sign distributing onto the final term. And what it's going to be is log to the base 3 of x minus 2 to the power of 1/5. And now I'm almost there. The last thing that I need to do is to bring those powers down. And that would be my final answer. So that would be that thing that we started with, fully expanded. So there it is as a whole, the entire thing. So that first term that we started with was very complicated and nasty looking. Again, just a reminder of the reason. To take a derivative of that first term would be awful. But the thing that we have in the very last line, taking derivative of that is very easy. And it will take you, I would say, once you reach logs in your calculus course, that final term, if you had to just take the derivative of that, that would take you 15 seconds. But that first term, more like 5 minutes, but you're also worrying that you've made a mistake or forgot something or done something wrong because it's kind of complicated. Now, those steps that I went through there, of course, they took a minute or two as well. I've gone through them kind of slowly because I'm demonstrating this expansion thing for the first time. But in my opinion, taking those few steps before you take a derivative is easier than not doing it at all and just starting the differentiation straight away. Okay, so that is using the log laws to expand the log expression to turn it into something simpler. There is another one just like that in the textbook. There's also change of base formula to do. Maybe I should keep going and see how you feel. I'm trying to decide whether to stop here or not. Again, can you tell me from 1 to 5, how do you feel about expanding logarithms like this? Fives and fours. Anybody else? Okay, that's solid. Okay, everyone's good. Okay. There's another example just like this in the textbook. This is only a slightly modified from an example in the textbook. All I did was put in that 3 there just so I could mention again that log to the base 3 of 3 was 1. So if you stop sharing here, and then I'm going to share something here. So you'll notice on page 112 here, the first question is basically the one that I just did, except I had the extra 3 that I highlighted. The second example here is the same, except this time you're dealing with base E, and you have a couple of E's in here that you're going to sort out. So if you're feeling good with it, almost everybody said 4 or 5. Make sure you read through this in your spare time, and I'll probably touch on it when we come back next week as well. And next week I'll finish off logs. I'm going to go through change of base formula as well, and we'll bring it all back then and solve some log and exponent equations. And then that will be it for logs. And we'll move on to trigonometry next week as well. So since we feel good about this one, I'm going to let you just read through that next example. And I'll stop class here 20 minutes early as a rare treat for you. I know I'm usually working right up to the last minute and sometimes a minute or two over. Any questions before we go? No questions. Okay. Okay, we'll end there. I've stopped the recording. I'll post the recording anyway.